Can we start? Okay, everybody, welcome to session 16. The title is Morphodynamics and Morphologic Models. We have two talks. The first talk will present by Professor Takebayashi, please. I'm sorry, my name is Shinji Egashira, the International Center for Flood Hazard and Risk Management, the Public Works Research Institute. Thank you.
Thank you, Chairman. Today my talk is about modeling bird and braided channels and unsteady flow condition and the effect of spatial temporal change of vegetation on bed and channel geometries. So this is a photo of Yoshino River in Japan. In 1981, so there are very few vegetation on the bird. However, in 2002, so most part of the bird are covered by the vegetation. And this is a cross-section of the Yoshino River at 70.6 kilometer and 20.2 kilometer. So in 1981, the cross-section shape is very mild. However, after 9 years, so sediment deposits in the vegetated area and the bed will degrade in the main channel. And after 9 years more, in 1999, that tendency is continued. So in the vegetated area, so sediment deposits more and more, and in the main channel, bed is degraded. So these kind of phenomena can be observed many all over Japan and also many all over the world. So many researchers are researching or working on so the interaction between the bed geometry and the vegetation. So in this research, we try to reproduce the braided channel and unsteady flow condition by the experiment and the numerical analysis. And in the model, we try to consider the invasion, growth, and the wash-away process of the vegetation. And we try to discuss the effect of the both unsteady characteristics of the water supply and the presence of the vegetation on the geometric characteristics of the bird and the braided channel. And in the model, so we try to consider the groundwater, so because the groundwater affects on the shape of the dry-bed area very well. And we also performed the numerical analysis of the bed deformation of the Yoshino River. And the Yoshino River is a real river. So when we perform the calculation for the real river, we would like to make a numerical grid, which is a boundary fitted numerical grid. So the equation in the model is written in the generalized curvilinear coordinate system. So this is a photo of the experimental flume. The straight open channel, the length of the channel is 7.5 meter and 1.5 meter width. And we supply the sediment and water from the upstream end. And we use the uniform material for this experiment, and the diameter of the material is 1 millimeter. So in the calculation, numerical analysis, depth integrated two-dimensional conservation equation of the mass and the momentum are employed. And for the conservation equation of the mass, we tried to consider the seepage flow here. And for the conservation equation of the momentum, effect of the vegetation is appeared here. So vegetation is treated as a drag force in this calculation. And for the bed deformation analysis of the braided channel, so for the sediment transport rate equation, the modified Ashita-Mitchell formula is used. The modification is made for the estimation of the critical shear stress on the slope. And for the vegetation model, so Tsujimoto's model is used here. in this calculation, we try to consider the invasion, growth, and the wash-away process of the vegetation. So we tried to change the vegetation density to reproduce that phenomena. So at the initial condition, so bed geometry is flat, so there is no bird, there is no dry bed area, so there is no vegetation. So but after the bed deformation, the dry bed area will be formed. So vegetation start to grow. We assume the vegetation starts to grow at the dry bed area. Then that vegetated area will be flatted during the flood. So but when bed is not eroded, so vegetation continue to stay there and continue to grow there in the model. However, when bed is eroded and the bed surface elevation becomes lower than the bed elevation when vegetation starts to grow, we judge the vegetation is washed away. So this simple model is introduced in the model, in the numerical analysis model. And for the numerical analysis, so this is a calculation domain of the numerical analysis, the rectangular open straight channel, same as the experimental room. And the water and sediment are supplied from the upstream end, and the bed deformation is calculated like this way. And so bed geometry, initial bed geometry is almost flat, so almost means that we add a very, very small disturbance to the bed surface, so like this way. So that side of the disturbance is the 10% of the sediment diameter. So let me introduce about the chaotic and the self-similar characteristics of the braided channel calculated by the numerical analysis first. So this figure shows a horizontal distribution of temporary change of the horizontal distribution of depth integrated water velocity. So this is each of them are velocity vector, but it is too small. So please judge the white area indicate the dry bed area, island, and the black area indicate the channel. This is a horizontal view. So, and this green arrow indicates the location of the local scarring. So at 3 hours, local scarring are formed here, and after 1 hour, the location of the local scarring is not migrate to the downstream, not migrate to the upstream. So if this bed geometry is the alternate bar, so maybe the local scarring will be migrate to the downstream at a constant rate. However, so dry bed area is formed. So this is a kind of a braided channel. So in this 1 hour, so the location of the local scarring will not migrate to the downstream, it will stay there. However, in the next 2 hours, this local scarring will migrate to the downstream rapidly. And the next 2 hours, so bifurcation is formed and the 2 local scarring will be formed. And in the next 2 hours, so upstream local scarring will be shifted to the upstream. So like this way, so temporary change characteristics of the braided channel has a chaotic characteristics. So this is another calculation result. This is also show the horizontal distribution of depth integrated water velocity. So in this calculation, we try to consider the vegetation. In this calculation, so okay, you can find many dry bed area here, but this dry bed area is disappear in the next 2 hours. And around here, new dry bed area is formed. So under this hydro condition, this multiple row bar approach to the dynamic equilibrium state. However, when water discharge is decreased to 67%, so for example, if we construct the dam in the upstream area, then peak discharge will be cut to 67%. So what will happen? Dry bed area will increase with time, and the location of the main channel will be unchanged like this way. So under this condition, so this bed geometry approach to the static equilibrium condition. So this figure shows the horizontal distribution of the vegetation density. So white area indicates the vegetation area, and the black area indicates the non-vegetation area. So when water discharge is unchanged, this vegetation is washed away, and the new vegetated area will be formed around here. However, when water discharge is decreased to 67%, vegetation area increase with time, and the vegetation will not wash away so much. Okay, let me show you the effect of the vegetation on the diversity of the physical environment in braided channels. This figure shows the relationship between the area of island and the existing rate of island. And this blue line indicates the power law. Okay, when we see 0.01 square meter for area of island, so we can get the value 2 for existing rate of the island. This means the two islands which areas are larger than 0.01 square meter exist in 1 square meter. So this is the result of, I'll show you later. This is the result of the experimental flume. So the scale is very small. So when water discharge is unchanged, the distribution of the existing rate of the island will be fit on the power law. So however, if the water discharge is decreased and the vegetation grows too much, so the distribution is like this way. So maximum size of the island will becomes larger more. And we can also see the flat distribution here. Flat means that there is no island which has this scale. So that means that if vegetation grows too much, so diversity of the physical environment in braided channel will be lost. Okay, let me show you the effect of the groundwater on the braided channel. So this is the result of the experiment. A blue dot indicates the experimental result. When we do not consider the groundwater, so for the smaller scale channel, so reproducibility is very good. However, for larger scale island, so the model cannot reproduce a large scale island. However, if we consider the groundwater, reproducibility for large scale island will be increased. So improved, so when we perform the numerical analysis without groundwater, small pond will be formed on the bar because the unsteady flow characteristic is formed in the braided channel. So, but in the experimental flume and also in the natural river, such kind of small pond, water in such kind of small pond will be changed to the seepage flow, groundwater. So, if we consider the groundwater, so reproducibility will be improved very much. And so next is the effect of the unsteady flow characteristics and the vegetation on braided channel. First, we performed the two calculations. One is for the steady flow condition, the other is for the under the unsteady flow condition. In these two calculations, we didn't consider the vegetation. Okay, this figure shows the bed geometry obtained in case 1 under steady flow condition. So under this condition, so many channels are formed. So it's a braided channel. So total amount of the water discharge is the same, but if we supply the water under unsteady flow condition, so sediment will be deposited on the bar very much because during the flood, sediment will be transported on the bar, and so small channel will be filled with the sediment. And on the other hand, flow will concentrate in the main channel, so the scale of the channel becomes larger, and degradation will be happening in the main channel. So same kind of phenomena can be observed in the experiment. So compare these two, so on the higher bed elevation area, so bed geometry tends to be flat, And in the main channel, so degradation will be happen in the main channel under unsteady flow condition. So next we try to consider the vegetation. Under this condition, these are steady flow condition cases, and in this figure shows non-vegetation cases. This figure shows we consider vegetation in this calculation. So as you can see, the number of the channel will be decreased like this way. So because vegetation grows on the bud and the sediment will be deposited there, and the new bifurcation will be suppressed in this calculation. And if we consider the both, so both mean the vegetation, presence of the vegetation and the unsteady flow condition. So under this condition, so on the bud, so many vegetation, so sediment deposition will be accelerated more during the flood. So sediment deposited on the bud very much. So finally, very clear meandering channel is formed. So like this way, so the vegetation grows on bud very well under this condition. So that will affect on the number of the channel very much, and very clear meandering channel will be formed. So these kind of phenomena can be calculated by use of the numerical analysis. Okay, let me show you the result of the calculation of the Yoshino River. So Yoshino River is located in the Shikoku Island, so south part of Japan. River basin area is 3,750 square kilometer. Length of the main channel is 198 kilometer. So all rivers managed by the government has designed high water discharge. So it's 18,000 cubic meter per second. And average river width is about 800 meters. So in 2004, Yoshino River had so many floods. So 1, 2, 3, 4, so 7 typhoons and 1 frontal precipitation. So until 2003, vegetation area increased year by year. However, in 2004, vegetation are washed away completely. So we picked up the 3 largest floods here. And okay, before 2004, so bed is covered by the vegetation, but after the flood, all vegetation are washed away. So to perform the calculation of the real river, so we would like to use the boundary fitted numerical analysis grid. So equations are written in the generalized curvilinear coordinate system, like this way. So it looks very complex, but the basic characteristics of the equation is the same as the original one. So it's a shallow water flow equation. So the mass conservation equation of the water, so we also consider the seepage flow here. And also vegetation effect is considered in the momentum conservation equation. And so now I show you only one equation for the momentum conservation equation because I don't have so much space. So of course this is a two-dimensional model, so there are 2 momentum conservation equations. This is the horizontal distribution of the vegetation. And this is the numerical analysis grid which is used in this calculation. So we performed 8 calculations, and for the first 5 calculations, we supply the water under steady flow condition. That discharge value is the peak discharge for each flood, and this vegetation density is calculated based on the numerical analysis. So this value is not a measured value. So I will show you what I mean. We try to get the vegetation density value, so by the analysis. So this figure shows the longitudinal distribution of water surface level along both bank, right bank and left bank. And for August 1st flood, in order to reproduce this longitudinal distribution of the water surface, we have to use 0.05 for the vegetation density. For the next flood, August 31, we have to use 0.01. And for the last flood, we have to use 0.005. So based on this calculation, so we can say the vegetation density decrease in a very short time because of the typhoon and flood and heavy rain. So then, in these calculations, so we didn't consider the height information of the vegetation. So, but in order to estimate the drag force of the vegetation, so we have to consider the vegetation height when water surface is lower than the top of the vegetation. So we can use the water depth to calculate the vegetation drag force. But when water surface is higher than the top of the vegetation, so vegetation height should be used to calculate the vegetation drag force. And in this calculation, so when bed will be aggregated, so under this condition, so vegetation height becomes shorter and shorter. That process is also calculated in this model. And for the Yoshino River and almost all Japanese rivers managed by the government, the vegetation, horizontal distribution of the vegetation is measured by the laser profiler. So today's calculation, I used this data in the calculation. So if we consider the height of the vegetation, we have to use much more larger vegetation density because so lower trees, lower vegetation will be covered by the water, so drag force will be decreased. Then on the other hand, so in order to reproduce the water surface level, so vegetation density should be increased. So we have not performed the field survey because this flood was happened between the big flood, so we could not get the data. So, however, maybe we are assuming, so maybe the vegetation density in the field must be 0.08 or something like that, and this value must be too small. Then, if we do not consider the vegetation, so of course the bed surface will becomes lower, and the difference of the vegetation. Difference of the water surface is about 1 meter or 1.5 meter. It's a quite large value. So, based on by use of these information, we try to perform the bed deformation analysis. And in the field, so we don't have so much information considering the invasion, growth, and wash-away process of the vegetation. And as I show you, so the phenomena in the Yoshino River was very quick. So in this calculation, we tried to change the vegetation density for each flood. For in case 16, for the first flood, 0.08 is used. And for the second flood, 0.02 is used. And in the next calculation, case 17, average value is used for both flood. And in the last calculation, we neglected the vegetation. And and in this calculation, we supply the hydrograph from the upstream end is like this one, like this way. So we focus on these two floods in this calculation. And in this calculation, so we treat the bed material is a graded material. So, but today I focused on the relationship between the vegetation and the bed formation process. I don't talk about the these models. So maybe Nuntio will talk about the model of the graded material. So I'll skip this talk today. But in my model, so yeah, today Annika talks about the stratigraphy. And also this model can reproduce the stratigraphy because we set many layers below bed surface. Okay, let me show you the result of the calculation. This cross-section is located in the downstream vegetated area. Yes, so downstream of the bar. So after the calculation, when we consider the temporary change of the vegetation, so bed will be degraded here and degraded here, and there is no bed deformation around here because this vegetated area located at the downstream of the bar. So when we do not consider the temporary change of the vegetation, in this cross section, so the difference is very, very small. And if we do not consider the vegetation, so of course bed will be aggravated like this way. So in the upstream vegetated area, so the difference becomes much more larger. So when we consider the temporary change of the vegetation, so sediment will be deposited near the main channel. And if we do not consider the temporary change of the vegetation, sediment also deposits here, but the deposition depth is smaller. The difference is 60 centimeter here. So this is a calculation only for 2 floods. So if we perform the much more longer calculation, so 5 years calculation, the 10 years calculation, so the difference becomes much more larger. So for the upstream region of the vegetated area, so the temporary change of the vegetation will affect on the bed deformation very well. And if we do not consider the vegetation, so bed will be aggravated in the main channel and degraded on the bar near the main channel. So bed slope becomes milder and the ecotone will be generated around here. Okay, in the end of my presentation, let me introduce about the IRIC, okay? So, don't stop. Oh, it stopped. Okay, our research group are making IRIC. So it's a free numerical analysis software of flow and channel deformation for low cost and high quality river regulation works for river all over the world to prevent flood and sediment disasters and to preserve the ecosystem in rivers due to the lack of the budget. So this is a free software. And for river researchers to perform the bed deformation analysis easily and develop our understanding of the phenomena in rivers. So IRIC is initiated by the researcher of USGS and Japanese many researchers. But now, many researchers are working on this project. So Deltaras, Tsinghai University, and River 2D. River 2D is also installed in the IRIC. So you can use River 2D through IRIC now. So I'll show you an example of the calculation considering the vegetation by use of my source code in the IRIC. We performed the calculation in the Mekong River. So this is actually not a gravel bed river. It's a very fine material, but I performed this analysis, so I'd like to introduce this one now. And this location is located near the national boundary between the Vietnam and Cambodia. And this area is called the Tan Chau area. So and a very severe bank erosion is happening here. So this is one of the most active channel deformation area of the Mekong River. And then the bank erosion happens very much, and the flood will also happen so much. So we consider numerical analysis grid is set on the flat plane also, not only for the main channel. Okay, and in this calculation, we set the vegetation on the flat plane and also in the middle bar. When we consider the vegetation, oh, it does not work. No. Maybe some has problem in the computer. I also know. Okay, so if I'll check the computer later, and if I can remove, modify it, I will show you in the discussion time or sorry. Okay, okay, I'm gonna skip the conclusion. Okay, and I'd like to say thank you for the, I got the research fund from the Japan Society for Promotion of Science, and I wish to acknowledge the helpful comment for the review of the paper, and also Professor Egashira, Professor Okabe, and Professor Fujita. Okay, thank you very much.
Thank you, Professor Takebayashi. And we will invite next speaker, the Professor Sibiglia at ETH Zurich.
First of all, I would like to thank the organizing committee to invite me here. It's a great honor for me to be here. And secondly, I would like to thank both my co-authors, Guglielmo Stecca and Astrid Blom, that both are here in the audience. So somehow the contents of this talk are related to the talk of Enrica Viparelli this morning. Actually, I will focus mainly on the active layer approach and how to model mixed sediment morphodynamics in gravel rivers using the Urano approach. The reason for that is that this model is the most widespread model used in commercial code. So there is the need of understanding how it works in detail, what you can get, what it is capable of which kind of process can describe. And then I will let you know, and I will add some drawbacks was already highlighted by Enrica this morning, and I will add some also. But I will show also when you can use it, actually. And quantitative predictions for mixed sediment morphodynamics, so have been advocated by different talks, in different talks in this audience, in this conference. And so I already, so I will review in this discussion, in this presentation, the state of the art of the theoretical and numerical developments in modeling mixed sediment morphodynamics using active layer approach. I will show some outcomes of a detailed mathematical analysis. I will try to explain why it's needed. And I will show some results from numerical experiments. I will end up with some conclusions in which I try to give, say, some advice on when you have to perform some numerical simulation using such approach. I don't go too much in the details of the model that was already presented this morning by Enrica, actually. And before starting the analysis, I will analyze the shallow water Exner model, essentially. And you know, here there are the equation, the governing equation of these problems. In 1D, you have three equations, essentially. This is the Exner equation. These are the two shallow water equations. And in the case, this model is used for homogeneous sediments. When you have, say, as in this case, mixed sediment morphodynamics, Irano put forward a model, developed this model in the early 70s. And actually, yeah, you have the active layer, you divide in two regions, and the bed, and you have an active layer, and here you have a substrate. And they exchange mass, as was already described this morning by Enrica. I don't give you the details here. Okay, finally you end up with a lot of many equations, actually, here. two for shallow water, one is working in the active layer, and one for the substrate. Actually, these two in the yellow rectangle, so in total you have 2n+1 equations that you have to solve. N is the number of fractions that you want to use for modeling. So n, if you have n is equal 1, you recover the Exner model. These are the closure relations that I use in order to produce these results. Actually, the sediment discharge of each fraction results from transport capacity for the case that the bed would consist only of that fraction. It's quite common closure. And I also consider hiding exposure as following the Jazarov closure relationship. And as it is made in many numerical simulation, numerical application of sediment morphodynamics, I assume that the thickness of the active layer is constant. And the porosity is also constant. This is a heavy slide. So in order to perform an analysis, I would like to perform an analysis of a small perturbation. I would like to understand if I put a small perturbation on the bed, where these travel. And I start with explaining what happens in this Exner model. Maybe this is trivial for some one of you, but it's needed for me to go ahead in describing the model of the Irano model. Actually, if you rewrite the equations in this manner, actually, and this is the case of two fractions, what you have is Q is your unknowns, water depth, discharge, bed elevation, and the contents finds in the active layer. So, and you have this matrix which contains, if you analyze this matrix, contains a lot of information. I will try to explain which kind of information are contained there. And let me start with the shallow water Exner model. So we have three equations. This matrix is 3 by 3. If you perform this difference, you end up with what is called a characteristic polynomial. Actually, this and lambda here, A2, A1, A0 are coefficients coming from, is a mixing of these coefficients in the matrix, and lambda represents what represents lambda, which is the physical meaning of that. So if you find the roots of this polynomial, and you can have some information. Actually, if you consider, let me consider a flat bed with a small perturbation on the bottom, very small. It is 10 minus 3 the water depth. Okay. Here I increase the scale. I distort the scale because I will show you something later. So that is needed for that. But this is the bottom elevation, actually, which is very, very small compared to the water depth. Okay. And it happens what arises from the analysis of the matrix. So if your lambda is greater than 0, which means that small wave propagates downstream. So at a certain point, if you leave to interact these waves travel in some directions. And these routes give you the information where these information travel, if downstream or upstream. Then in the next slide, I will present the results in terms of lambda star, which is, say, dimensionless value of lambda, of the eigenvalue, actually, of the wave, the celerity of small perturbation. And if it is, this value is greater than 0, the small wave propagates downstream, is less than 0, propagate in upstream direction. Okay, you end up studying the shallow water Exner model, you end up with such a graph. You have Froude number, and here you have the lambda star, which is the dimensionless wave propagation. So, and what you can see here is that essentially that you have two roots. I call you these are the roots of the polynomial, and then you have here, say, a positive, 0 is here, and then you have a positive value and a positive also here. And then you have a negative characteristics. So essentially what is predicting this is that you have two information traveling in the downstream direction and one traveling in the upstream direction. Let me show with an example. I take the example that I shown before. Flow number is 0.75, so we are in the subcritical region. And now I will run the movie. Please check, have a look here at the beginning, this region. You will see a very fast wave rising from. It's working? Yeah. Yeah. Then at a certain point you have a wave, you see a wave traveling in upstream part, and then you see that the bed is slightly moving in the downstream direction. Okay? So the first fast wave is related to this eigenvalue, to this characteristics. So, and this is actually the other one. This is negative. Is the one propagating in the upstream direction, and the bed essentially is moving with this velocity, which means that you can see here in this region is traveling much slower than the other two waves. There are other information that I would like to remark here. That's this downstream propagating wave, the fastest one, is translating downstream all information concerning bed change variations. While, and the same applies to the one propagating the upstream direction. While the red one is mainly related to the bed. And then if you, okay, let me show this once again. So you can see here this wave and nothing happens here. Then you can see this other wave, which is this one, and nothing happens on the bottom. So it's too fast to trigger a variation in the bed, actually. And the bed is traveling downstream, and then while it's traveling downstream, it changes also the bed, the water depth. Let me come to, let me consider now the 1D shallow water Exner-Irano model. Two fractions, only two fractions. So I have one equation more, so I have the characteristic polynomial is the fourth order. So I have four equations and four roots, and these are the results actually. You can see that the blue one and the green one are more or less the same that we get before. So they are the one related to the water depth variation. But there is a new wave arising, this gray one, which is what we call sorting wave. And yeah, if you zoom in that area, you see the red one is what we call the bed wave, and then here this is this is the sorting wave. What we found in analysis that we performed with Guglielmo and Astrid is that always. Actually, Riebering did in '97 an analysis, and showing that the mean diameter, so the mean distribution of that, is traveling in the downstream direction. We had more fraction, and we demonstrated that all these sorting waves travel in the downstream direction. Are always, so these characteristics are always positive. Then let me go to this example. So now I have a flat bed and a flat water depth on top of that. And I have here a reference, a 50% of fines, a 50% of coarse in the bed. I perturb a little bit the distribution. Yeah, it's very tiny, from 50 to 51%. So I'm studying small perturbations. So, so what I expect is that many waves arise in the pattern. So, and then the sorting wave will travel in downstream direction. These are the results that we get. Here is not a video, it's only visual. So the fastest wave the one related to hydrodynamic, is already gone, is out of the domain. The other one is here, actually, and you can see a small perturbation on the water depth. You see water depth here, bed elevation, and the content of fines in the active layer. You can see that you don't have any variation here. And here you see that there is what we call the bed wave. Actually, the bed wave is you have a change in the bed, you have a change in the water depth, and you have a tiny, very tiny difference in the active layer. Why? Well, this is the sorting wave. The sorting wave in this case is faster than the bed wave, and it carries information of a change of grain size distribution, but also a change of bed elevation. So if I extend this to 5 fractions, I have 5 fractions at the beginning, so same configuration with 5 fractions. And what I see here, that I have this bed wave, and I have other 4 waves, which are sorting waves, which travel different speeds, and they trigger a variation on the bottom. So let me point out, I would like to make a consideration about the propagation velocity on small perturbation, as I would like to compare the bed waves versus the sorting waves. Okay? And Riebering, as I mentioned before, he performed this analysis, and he ended up with approximate values of this, say, the wave, the celerity of the wave, of this small wave. So, and he ended up with this. He concluded that this ratio can be in the range between 0.2 and 4, which means that the bed wave and the sorting wave can be so the bed wave can be faster or slower than the sorting wave. It depends. It depends, as I show here, mainly, these are the main parameters between the ratio between the active layer and the water depth and the fluid number. And this is, DSM is the mean diameter, but this is not, does not play a big role on that, actually. This is, I can show you, I recall you what I get before, and here we have a, say this is the sorting wave, which actually does not change. It seems to be constant, the propagation, the velocity of propagation with fluid, with the fluid number, and while the bed wave is changing its velocity with fluid number, at a certain point there is an intersection. And yeah, at this point they become, they can become, say, they have the same magnitude. Now let me, yeah, I mainly develop numerical models, and I'm in the group of Favi in which we develop this basement. And so I keep an eye always on numerics. Actually is really important. Let me brought out my point here. Actually, when I have a model, now what I describe is the physical behavior. I have a model actually with equations, and these equations are telling me something about the processes. Okay, and if you want to extract everything, all the information that you can get from this model, you have to do a good job from a numerical point of view. So, and also the analysis that I presented before, it goes in this direction. More information you know, more accurate can be your numerical solution. Okay, that's and let me start this with at the last GBR7. I get this statement from the paper of Mosselman. This was the last statement in this paper, and he said that the challenge for modeling testing is the development of a set of elementary validation cases that, along with the corresponding criteria for acceptance, which is agreed by international fluvial morphodynamics community. So I would like to stress that I point out that this part is really relevant, actually. So I'm going to show you some of these elementary validation cases that we use for understanding at which extent the solution, the numerical solution obtained with this model are reliable. First of all, I showed this simple example. With this analysis, I didn't give you the details, but with this analysis, I can end up with an exact solution of my equations for small perturbations, which is actually the fickle line. Okay, if I have a so if you give a mathematical model to an applied mathematician, he doesn't care about the physics which are there. You say, give me the equations, and if it's possible, we can derive the exact equation, exact solution, and then I compare my numerical solution, because I have to approximate my equations to solve the problem, and then I compare with that. So actually, the approach that I developed, that I showed you before, allows to derive this extra solution that can be used for assessing numerical performances of different numerical schemes. And in my field, this is quite relevant, actually. And now I go to I'm going to show you some results obtained with a code developed by Guglielmo Stecca, which is here in the audience. And this is experiments put forward by Riberink in 1987. We have two sand fractions, constant slope at the beginning, and this is the ratio of the active layer to the depth, and fruit number is, we are in subcritical conditions. So we have an initial configuration, which is actually almost flat bed with some dunes over there, but we can, in the numerical simulation, in 1D, you consider which is flat bed. So you have at the upstream boundary condition, what he did is that to decrease the contents of fines, okay, and the fines goes from 0.45 to 0 in 30 hours. So essentially, but the solid discharge at the input, at the inlet remains constant. Okay? Essentially, what he did is to introduce in the system a coarsening wave, which can be interpreted as a sorting wave, somehow. Yeah, you can see, you can compare here the red. The bullet are the experiments, and the continuous line and the numerical results. Please not consider this solution at time after 10 hours, because there are some problems related to the experiment. And you can see here that actually the model is capable quite reasonably well to detect the downstream sorting variation. And and I will come back to that. There's an increase in the time, so the solutions are more spread. Then, if you look to the numerical and also to the experiments, you can see that there is a nick point here, and this nick point is where the content of fines in the active layer changes. So. In my view, is the place where the sorting waves arrive. So the coarsening arrived there. And then, yep, you can see that this nick point. And so I can interpret this as a sorting wave, which changes the contents of fines, the grain size distribution inside the active layer. And can we, if we estimate the sorting wave speed is more or less from the numerical results and from the experiment is more or less 1 meter per hour. And if I use the Riberink, the analytical Riberink expression, well, we end up with this number, which is very close. One of the problems that is that affects quite a lot the Irano model is the description of the vertical distribution of the grain size. So here you can see that this is a vertical distribution, the active layer, and see that the numerical experiments and model here are quite in good agreement, while here is performing a really poor job. And this is so, this shortcoming is potentially severe also for longitudinal sorting on a longer term. This is that's why we explain that this, say, the increasing of the mismatch, the mismatch increasing in time between the numerical solution and the experiments. Yeah, this is. You can see here you are very close, and then starting here you are very, very. So you start to see some problems there. And then maybe this is due to the fact that due to this poor description of the sorting in the substrate. Briefly, so there are some other models that can be used. They were tested and developed by Astrid, that they overcome this problem. As you can see here, this is the Irano model. It's more or less this, the results that we get, and then here a model developed by Astrid. You can see that this is the measured one. This is the one obtained with the model, and they are quite in good agreement. This model is doing also good job in the substrate. But yeah, implementing this is cumbersome. You need small time steps, and so you need very long time step for integrating these equations. Finally, I'll concentrate on quite mathematical aspect, but which has a lot of implication for numerical simulations. In the case of, no, this is wrong. In the case of two fractions, okay, Irano model, so you have this polynomial. If the roots of this polynomial are real, all real, as I showed you before, all the cases that I showed before, these are all real. And so you can, the mathematical problem is hyperbolic, and it can represent time marching problem. So it can detect morphodynamic variation. If the roots are imaginary or complex, if they are complex, the mathematical problem is elliptic, and it's not anymore suitable for describing time marching problem. And actually, here, ignore the other lines, focus only on that. These are this is a fruit number, and this is the lambda. These are the roots, the non-dimensional roots. And we didn't plot the roots when they become elliptic. So there is a region here. You can see here are real, and here are elliptic. You don't have any. And yeah, which are the consequences of that? We run this simulation here. We have M2 backwater profile, and then we have a coarse mesh, a coarse bed, which degrades in a finer one. And you can start to see such a behavior. And when you have a degradation and you degrade from a normal layer to a final one, these problems may be severe. And then you end up with funny things, waves, traveling upstream, downstream, and then you maybe can discuss about that from a physical point of view. But it's a fake, actually. And yeah. let me draw some conclusion here. So what I show you is that the mathematical model predicts the presence of sorting wave, which travels always in the downstream direction. We have propagation velocity, which is often, but not always, larger than the bed wave propagation velocity. The choice of the active layer thickness is relevant, plays a major role in the observed results, always. So when you run a simulation and you decide an active layer, this will affect very much your solution. Yeah. So numerical accuracy also, given the complexity of the model, deriving good numerical schemes for solving more or less exactly the equations plays a fundamental role. Say more accurate, as much accurate as possible. And the active layer model is adequate for representing streamwise sorting, but only when vertical sorting does not play a fundamental role. And under degradation into a substrate, which is finer than the active layer, the mathematical model may switch its mathematical nature, giving rise to, say, funny results, but which are not reliable at all. Yes, that's fine. This is all. Thank you for your attention.
Thank you, Professor Siriglio. By the way, can I ask you to share 1 or 2 minutes for Professor Takebayashi? His computer was already recovered, so I asked him to show some remaining result. Okay? Okay, good. Thank you.
I'm sorry. So maybe it will work. Yeah, I think so. So yeah, we set the vegetation on the flat plane. Okay. Okay. So in this calculation, so we consider the vegetation. So sediment deposits on the flat plane. So red indicates the sediment deposition. And for the, if we do not consider the vegetation, so flat plane will be eroded like this way. So, and okay, it takes some more time. Oh, for the so this model can also can perform the calculation of the mean diameter, size distribution of the bed material. Then so these areas, so sediment deposits around here. So around here, bed material becomes finer. So these, so simple tendency can be reproduced by this model. So at the present, so the model in the IRIC cannot consider the dynamic state of the vegetation. So it's only the static condition. So, but in the future, so we'd like to remove, improve our model and try to consider the temporary change of the vegetation in the model in the IRIC. Thank you.
Okay, thank you, Professor Takebayashi. Okay, so let's start to for the discussion and the comment. Please. Okay, please.
Bill Dietrich, Berkeley, thank you for 2 excellent talks. I have a short question for each. In the model you just showed us, is there, if you ran it for a very long time, would there be a stable state arrived at where the vegetation has fixed and a channel is fixed and it no longer, the vegetation no longer, the system is no longer building up? Yes, it's for him, and then I have a question for you.
Yeah,
so,
I can also do this question.
What's that?
He can also answer. Nice.
Okay.
Okay, so it depends on the hydraulic condition. And so for the calculation of the braided channel, so braided channel will approach when so water discharge is enough large and the vegetation will be washed away sometimes and invaded sometimes. In that case, so braided channel approach the dynamic equilibrium condition. So some vegetation will be washed away, the new one will be invaded. So then the total area of the vegetation will not change with time. Yeah, so there is some disturbance, but for a long time, average, no change. Such kind of condition can be formed, and if we supply the smaller water discharge, so at the initial stage of the calculation, vegetation area will increase with time, but approach to the equilibrium condition. So in that case, so on the bar, vegetation, full of the vegetation, but cannot grow anymore. So in that case, so river will approach to that condition. That's okay?
I had a question.
And actually, we take this problem, and also we have a model for that, and the results will be presented by Walter in the next section.
So my question for you is, maybe you explained it and I didn't get it, but what exactly is the mechanism that causes a sorting wave to happen as it's connected to an active layer? What is happening there that causes a pulse downriver?
The cause is that essentially, if you think in, say, you have, for example, two external equations there. We want each one for each, yeah, and then these are not balanced, and then you end up with a variation on the bed elevation that triggers also, and then the process starts from there. This is.
But is it that there's a different speed and downslope movement associated with the two sizes?
Yes.
And that's related to its relationship to excess shear stress? Is the sorting wave led by the fines or the coarse? Is that what you mean by sorting, that there's actually a lateral as compared to vertical sorting? I'm just not exactly sure what it is you're describing when you call it a sorting wave. Is it, if I were to see this, would it be a coarse fine, or do you mean laterally, or do you mean vertically?
What I show is the downstream, the downstream sorting. So
Right.
our downstream weight traveling downstream direction.
So does that mean that one size moves faster than the other?
Yes, of course.
And which size is that in your model?
Which size that? I don't know if I can reply to this question, and also the model. I don't know if you can say that, because there are a mix of information. So you end up with these 5 waves, but there is a mix of information coming from all the fraction. I don't know if the model can say to you which fraction is traveling at that speed.
Okay, thank you.
Yeah, if I could add to the discussion, please. Actually, when you put a local variation in one of the fractions, you actually perturb them all. And the waves which are triggered, each one takes a perturbation in them all. So it's quite tricky to assign a sorting wave to a particular fraction. It's actually impossible. In the results which were shown for multiple sorting waves, you can easily get that any of the peaks in the content of any of the peaks, actually any of the Gaussian variations in the content of fraction in the active layer collect variations in all the fractions altogether. So that's what I can add as a quote of the thing.
Okay.
Thank you, Philippe Beledi, Grenoble University. I would just begin with the question I had about this propagation. Trying to explain this to students, I'm always the trouble of finding a real example of this sorting propagation upstreamward and downstreamward. Is it possible to find one?
What I show in the ribbering example. Yeah, this is actually you see this information.
Yes, but it was a numerical evidence.
No, actually, it's also experimental evidence. So you can see that. This was our interpretation of the result. Actually,
No.
Actually, this is a good example, but you can perform other different experiments in the lab. Maybe they are already available.
Okay.
Okay.
Thank you.
I answered your question, more or less.
I have not the example in supercritical flow, but I guess...
Supercritical?
Yes, in supercritical, I guess it's even more difficult.
Yeah, I guess
More
so.
tricky.
Yeah. Because the waves are also faster. It depends on also how much supercritical is. Because if you are close to the critical condition between say what we say between 0.8 and 1.2 in Froude number, so the waves are it's messy, and they are very fast. Also, the water depth waves, the perturbation of the water depth travels the same speed of the perturbation of the bed and also the sorting wave. So you have to go very far.
Yeah. And I had also a very short question to Hiroshi Takebeshi. It's how do you share the friction slope between the drag force in the vegetation, between the drag force and the stress on the bottom to compute the sediment transport?
For the sediment transport, we will use the shear stress on the bottom only. So because the drag force of the vegetation will not work to transport the sediment, so we are using a kind of the effective shear stress to calculate the sediment transport rate in the vegetated area.
Peter Nelson, Colorado State. In response to this comment about the example of sorting waves, I think a really good example might be bedload sheets that Jeremy Venditti showed a schematic from Peter Whiting's work in his talk yesterday, or was it yesterday? Tuesday, whatever day. We've done some experiments. Bill and Hiroshi Ikeda and Fujika Seiya and Jim Kirchner did experiments in scuba in the 80s, showing how bedload sheets are basically these downstream propagating, coarse, fine, they're sort of like bed forms, but they're not very big. They're primarily a sorting feature, and in the 90s, Giovanni Seminara and colleagues did an analytical analysis on what I think they called sorting waves.
Bedload sheets.
Bedload sheets, and
Colombini, Seminara.
Yeah, Seminara, Colombini, and Tubino maybe, I can't remember. Anyway, Parker, Barry Parker, of course. So my recollection from Giovanni's work is that he demonstrated analytically that the roughness feedback from the perturbation in the grain size, so having an increased concentration of coarse particles, say at one location of the bed, that feeds back into the vertical flow structure, which then feeds back onto the sediment transport rate and allows that perturbation to propagate downstream. And that's potentially one explanation for how bedload sheets might form. Another explanation, which we tend to think is dominant, might be a particle-particle interaction that we've talked about quite a bit this week. So you're probably familiar somewhat with Giovanni's work. I'm curious, how does what you presented today relate to what we already know about bedload sheets and that kind of phenomenon?
I discussed that with Marco Colombini also. Actually, the 1D model is not capable of reproducing these bedload sheets. So you need more complex. I don't know. I don't remember. I think that Giovanni and Marco use a 2D model for doing that, actually, because to take into account, 2D like that. So this is not enough to see that one, to this such a behavior.
Marco Redolfi from the Trentos University. I have a question for both. You, Hiroshi, show us that with IRIC, you can model very easily, very, very complex morphodynamics, braided river with vegetation. And on the other side, Nunstio showed that even a very, very simple case of a 1D Hirano model can lead to very, very problematic numerical issues like very needs of very short time step and even instability in case of elliptic problem. And can you briefly comment this?
What? Comment for the...
Yeah, because it's very interesting the overview you both give, but since you feel this really different difference between the two talks, I want just a brief comment.
The first is maybe the Nuntio's model is also complex, I think so. Then sometimes I will use the same kind of relatively simple model comparing to our model, but our model is still simple comparing to the other model. So the toughness model is very simple in the model. So so maybe all model has a purpose. Okay. So for example, for the reproduce the braided channel. So if we use the three-dimensional model, maybe we cannot produce the braided channel. So it takes a very long time. So for the alternative bar or very simple so the braided channel, so maybe two-dimensional model must work very well. But if we want to perform the very long time calculation, a long reach, so ALGO cannot work. So too heavy calculation. So at that time, so maybe we had to better use the Enrica's model or the Nuntio's model, or then so yeah. Is that answer for your question?
Yeah, it's a very tough question, but thanks.
Okay, if I get right your question, so I think that for arriving to the model that he presented here, and also the model that Walter will present later on, and also all the models contained in IRIC, there are some steps to arrive there. And so the knowledge of the basic features contained, the basic processes contained in the model, in the model that can be studied with the approaches that I show you, can tell to the numerical guys something. Okay? For example, say when you have to put where you have to put the boundary condition. Once you know where the waves travels, you know if you have to put a boundary condition in the upstream part or in the downstream part, for example. And the knowledge of you know, sure. And in order to develop new numerical schemes, because always I sit in a table, we're talking with users of our code basement. They ask, oh, I want that the model is very accurate and it's really fast. Okay, this analysis will let me and the others to develop new numerical schemes that allow to answer to engineering questions.
Thanks.
So my question is follow Peter's question. For us, when you're talking about the sorting waves, the first impression about such kind of things is Banner sheet, and I think for most of people will think so. The problem you just told us, you say your one-dimensional model may cannot repeat such kind of bad form, but actually I think one-dimensional model is enough. If you treat the different transport the equation or the roughness of the bed surface, as long as the different fraction of the coarse and the sand are different, and you treat different band transport rate, and you will find such kind of bed form in one-dimensional model. That can be done. This is the first. And the second is, in your paper you said the sorting waves may, and most of the time, were faster than the bed form waves. And that is very interesting. Because for ballow sheet, for dunes, for all such kind of things, the bed form are strictly linked to the sorting. Because like the ballow sheet, the head is more causing than the tail. and you never find the tail is coarser than the front. And the same thing had happened for the dunes, and you may find the dunes may be coarser at the head of the dunes and finer to the tail, and you never find the reverse trend. So I'm not understand why you can find such the sorting waves move faster. How can you find such things in reality? And the binary sheet should reflect what you said, the sorting waves and the binary waves. I think they closely related.
I will try to answer to your question. But, as I showed you before, that it's the ratio between the velocity of propagation of the bed wave and the sorting waves can be greater or smaller than 1. Depends on the choice that you do for the active layer thickness. But if you want to predict, say, bed dune evolution, this is not the correct model for doing that, because you cannot get this information with this model.
So I would like to add to the point raised by Bill Dietrich. So it's more a comment than a question, maybe. I would interpret the bed wave as a wave that is mainly induced by a gradient in the transport rate, in the total transport rate, while a sorting wave is a perturbation that migrates primarily through a gradient in the transport rate of a certain size fraction that is caused by a spatial gradient in the bed surface grain size composition. And as such, as the origin is a spatial gradient in the bed surface grain size distribution, such a sorting wave cannot occur if you deal with a model that is based on Saint-Venant-Exner. So it's attributed to a spatial gradient in the bed surface grain size distribution. And a nice field scale example is the case where you consider coarse sediment augmentation, as they are doing as they're presently conducting in the German Rhine. So if you add coarse sediment to a certain river reach, the bed surface is locally coarsening, and you limit the supply of sediment because of the coarsening of the bed surface. You limit the supply of sediment to the downstream reach, and that spatial gradient in the transport rate, the downstream decrease in the transport rate, causes a degradation wave that precedes the local aggradation wave that is induced by the coarsening. So this also explains the fact that such a sorting wave, the small degradation wave that can precede an aggradation wave, that it is faster than the bed wave.
Yeah, and we discussed yesterday. We agree.
Watanabe from Kitami Institute of Technology. I want to ask to Professor Takebayashi. When we consider the channel formation in gravel bed rivers, we should consider the bank erosion. What do you think about that, and how to treat the mechanism in your model?
So bank erosion must be a very important factor to calculate the bed deformation process or also the channel deformation process. So in this calculation, we are using a very simple model. So we are considering the angle of repose, and the sediment will be slide from top of the bank to the bottom. So then for the calculation of the Yoshino River, so honestly, so the scale of the mesh is relatively coarse, but it's not a braided channel. It's weakly meandering channel. So I think that on the slope, we can set some numerical analysis grid mesh. So I think that it can be reproduced. And for the braided channel calculation, so I show some result of the calculation, but that calculation is for the experimental Froome scale, and we set the 1,000 numerical mesh in the transverse direction for, much more smaller. Sorry, in today's calculation, much more smaller. But so we set many numerical grid on the numerical grid. So we hope this model can reproduce the braided channel well. However, as I show you, so braided channel has self-similar characteristics. So for small braided channel, so we cannot reproduce because of the cost of the mesh, and also we cannot reproduce the bank erosion process by the small channel. So, but already we are taking care of the scale of the numerical grid to reproduce the bank erosion process. So that's a very important point, and we have to consider the subgrid scale phenomena to reproduce a good bank erosion process. Thank you.
Any other question? Comment? Okay. So thank you again for the two speakers and the colleagues joining discussion. Thank you very much.